So now we shall be talking about high level synthesis. Now as I mentioned in our last class, basically high level synthesis means that starting from the behavioral specification you are trying to arrive at a register transfer level netlist for the given design, and in fact you will see that in order to do this transformation there are a number of different steps you have to go through. Most importantly, you will have to understand what is the kind of intermediate representation or intermediate form that we need to represent our design specification in, so that it is easy to manipulate. So, first let us talk about the design representation. We will try to illustrate this with examples, and subsequently we will see that using this design representations how we can do a number of different manipulations. So, of course, this representation will be essential for efficient processing for obvious reasons, and our input that we are feeding is some hardware description language, behavioral description. It can be Verilog, VHDL or any other language. So, our first step will be to translate this into some canonical intermediate representation, okay, which will be easy to process and efficient to represent. Now, this canonical representation should be such that it should not be dependent on any particular hardware description language. This is of course very important from the point of view of portability across CAD tools. Suppose you have one part of the design coded in VHDL, other part coded in Verilog. So, if the intermediate representations are the same, you can mix the designs and you can synthesize them. So, this intermediate representation should be language independent and should give an uniform view across a number of CAD tools and systems. And the typical synthesis tools which work on a design for synthesizing will be working on this intermediate representation and will be carrying out several transformations on them. What I am saying is that suppose I have an intermediate representation version I. From there some CAD tool will be transforming it into another intermediate representation version J. Okay, representation will be the same, but we will be carrying out a sequence of transformations on them, so as to, you can say, improve the performance of the resulting hardware that we will be getting finally. Okay. So, let us very briefly try to understand what is the scope of high level synthesis. Now, here from this diagram you can see that we start with a behavioral specification in a hardware description language, Verilog, VHDL or any other language. From this we come to the intermediate representation, which is CDFG. This is the most popular representation which people use, control and data flow graph. See, as the name implies, it is not a single graph, it is actually two graphs, control flow graph, data flow graph, but the both of these two taken together, this is called CDFG. So, this transformation step is needed at the beginning, and from this CDFG there are a number of sequence of steps you need to follow, through which you will be synthesizing the basic hardware comprising of the data path, that means the arithmetic logic unit, bus, registers, etc., and also the circuit which will be controlling them, that means an FSM controller. There are again several steps that have to be gone through. The most important of these are scheduling and allocation. There are other steps also, we will be talking about them later. So, as you can see from the given description, we will have to carry out a number of intermediate steps. Finally, we will be arriving at a data path structure and an FSM controller. So, at this stage we can say that our hardware has been synthesized. So, we have the basic hardware ready, we also have the control unit which will be controlling the hardware, both are there. Typically from CDFG we separate out FSM and data path and synthesize them separately, because the way they are synthesized or the kind of you can say the basic building blocks you use in them, they are quite different. Okay. So, let us first take some examples and try to illustrate how this intermediate form looks like and what is the control part of it, what is the data flow part of it, alright. So, let us take a very simple example. Suppose there are 3 statements in a description language. I am not talking or concentrating on any particular hardware description language, this can be any generic description. B, C are 2 values typically stored in registers, they will be assigned to A after adding, A plus C assigned to D, D minus A to X. This is in sequence. So, the value of A which is getting here, that is used here, D computed here will be used here. Okay. So, now let us see how this particular thing can be mapped into a data flow description. Okay. First, I am trying to draw the data flow description. Data flow description will contain each of the intermediate steps which you need. You see, the first statement takes B and C as input and compute A. So, I am trying to show that part. It reads the value of B and C, it performs an addition and it writes it into A. This is the first statement. This corresponds to the first statement. Similarly, you have the second statement where the operands are A and E. You do an addition again and you compute the value of D. So, this is the second step. Similarly, third one you see, the third step is x equal to D minus A. So, in the third step you read D, read A, subtraction, this is the operator, and write into X. See, these are the 3 statements corresponding to which these are the data flow graph. This is called the data flow graph. This shows how data flows through the operators. And another thing, these are the individual data flow graph for the 3 statements, but we have not told or mentioned anywhere that these 3 statements have to be executed in sequence. So, in addition, there has to be some kind of a specification that this is statement 1, this is statement 2 and this is statement 3, and the statements must be executed in sequence. This corresponds to S1, this corresponds to S2, this corresponds to S3. So, this simplistic description, the portion on the left where you are saying that this S1, S2, S3 must be executed in sequence, this is the control flow part of it. Here where we are talking about the actual data, reading and writing from registers, doing the operation, adding, subtracting, this is the data flow, right. So, these two taken together will give us the total picture. See, but I am also illustrating with respect to this example that during synthesis this intermediate representation is the first step, but this is not the end of this, end of the story. Just you can carry out very simple manipulation on this, keeping this control flow description in mind and carry out some optimization. What I am saying is that this DFG can be optimized looking into the fact that S1, S2, S3 has to be executed in sequence, and you can get an optimized version like this. I am showing this. B and C are read first, they are fed into an adder. Okay, this write A, immediately you are reading A, so you need not store it anywhere intermediate. You can straight away use the output of the adder as the input to that. So, if you have another adder, the first input to the adder can come straight away from the output of this adder. The other input is E. And similarly, this D straight away you can feed it to a subtractor. Of course, the output of the subtractor is X, write X, but the other input is A. A is this same value which you have computed here. So, this same value out here, this will also have to come here. So, this is the modified and the compact data flow graph for the same problem. Now, these are techniques which are already used by compilers, and these are fairly standard techniques, that you have several statements, you just parse them, try to minimize them, you try to minimize the number of variables you required for execution. It is like that. This A and D are really not needed. Straight away the output of one can be fed to the input of the other. So, this is a very simple example I have taken, just assuming that there is a sequence of statements to be executed, the data flow graphs, and how we can go about constructing the data flow graph.
Like in the second one, the second graph, we have implicitly included the control part in the data.
Yes, yes, we are using the control information for optimizing it. If the control stuff said that these three are concurrent statements, then we could not have combined it like this. So, implicitly control information is also used to carry out this minimize. Huh?
Like this modified one is still, we call it a data flow.
This is still a data flow graph, but this data flow graph also keeps, you can say, it is consistent with the control information which was specified. Okay. So, this in a sense it combines the control and data flow together, you can say.
How do you think the statements have to be executed one after the other? As from the
No, one after the other, the way we have drawn the data flow, see, if you simply follow these arrows,
that is right, sir.
that
From
is,
the behavior description.
No, I am assuming that the hardware description language in which you have written this specification, these three statements mean that one after the other they will have to execute it. That is the assumption I am making. Okay. Now, let us take a slightly more complex example, where there is some control, not just simple sequence of execution, there is some if then else kind of things. Here we have a case statement, and if the value of C is 1, you add 3 to a variable x, you use the same value of x, add 1 to it, write it to A. If it is 2, A equal to x plus 5, and otherwise A equal to x plus y, right. Now, in this case you will have to explicitly specify the control flow graph, because that is important, because here the control flow graph will have to check for the value of C. Data flow graph will contain this information, but the actual data is flowing register to register, addition, subtraction, etc. But control flow graph will specify that I will have to check the value of C. If it is 1, call that, if it is 2, call that, if otherwise call that. Okay. So, let us try to show that diagram. First, the case statement C will check 1, 2 or default. So, this we are, or this is typically represented like this. This is a case block where there are 3 branches out, 1, 2 and default. These are the values. So, if it is 1, you will be executing a block B1. If it is 2, you will be executing a block B2, otherwise block B3. Now after that, again the control will be merging these 3 traces and it will be single trace of control will emerge. Now, this is the control flow description. Now, control flow description actually this will be checking the value of case. So, there will be some kind of a multiplexer or a decoder out here. It will be checking the value of the variable C. Depending on the variables, the value of C, it will be generating control signals to activate B1 or B2 or B3. Now, this is only a part of the story, this is not complete. Now, in order to complete it, you will also have to show the data flow part. Like the first data flow part will be read C. This is one data flow description. This will be linked with this because the case statement is working on C. So, we will have to read the value of C, that is a data flow operation. So, there is one data flow block out here which is assigned to this node of the control flow block. Similarly, okay, I am showing it for B3, I am showing first. B3 is A equal to x plus y. So, it is similar, read x, read y, add them up, write A. So, this is your B3. So, generating control signal for B3 means you are activating this piece of the hardware. Similarly, for B2 it is A equal to x plus 5, read x, the constant value 5, add them up, write A. This is for B2. Similarly, for B1, B1 is a two statements, x equal to x plus 3 and A equal to x plus 1. So, this also similarly you can have, you can combine, I am combining them straight away. Add x and 3, write x, and the same value you can take directly from here, you can feed it to another adder with a value 1 and you can write it to A. So, this corresponds to B1. So, this part is the data flow graph, this part is the control flow graph. So, actually the high level synthesis system will be first parsing your behavioral description and will be generating both the control flow and the data flow. Data flow graph, once you have generated diagrams like this, there will be some processing on this to find out how many registers you require, how many arithmetic logic units, adders, subtractors you require, what is the kind of hardware sharing you can use, what is the total number of computation steps or the clock cycles you need. That is the design of the data path. But once it is done, the control unit, this can be implemented as an FSM. The control unit will be simply generating the control signals to activate the data path, right. So, these two descriptions are generated concurrently so that they can be synthesized also together, right. Yes.
So, only one of the B1, B2, B3 will be executed.
Yes.
So then, like, why do we need one more control block?
One more control block means
So below B1, B2, B3.
this one. This is not really a control block. This is like a connector notation. That means depending on some condition, you are doing one of many things, and after you have done one of them, you again come to the same point, and from there you continue. This is just a flow of control. Control flow, there is a single thread of control which is there. So, beyond the point there is an if then else kind of a thing, you go to one of them, again you come back to the same point and continue from there. Yes sir, nothing else.
Here from control you have given a signal to read C. Now that C should again come back to the control and then the control decides which one to select.
Yeah, because this case block, this block with an array to it implies that the data flow block where you are giving the signal, the value coming out of it will be used here.
Okay,
That is implicit. So, these notations mean something. This is a case notation, case will imply something. You are computing some value, that value will be used to take the decision. There will be some comparators also here. Okay. So, let us take another simple example. So, this is not a case, this is an if statement. If a variable x is 0, then you compute a equal to b plus c and d equal to b minus c, otherwise d equal to d minus 1. So, this is also very similar. In fact, this is much simpler than the earlier example, and I am showing the picture. If x equal to 0, a equal to b plus c and d equal to b minus c. This part is shown on the right side here. This is the x equal to 0 part, and you look at the control flow part, there is an if statement. So, there is a condition evaluation. Now, condition evaluation, what is the condition evaluation? It is if x equal to 0. Now, x equal to 0, you can see this is also a part of the data flow. Read x 0, compare, compare is the operator here. So, the value of this is evaluated and this is used by this if block to take a decision. The value will be either 0 or 1, false or true. So, if it is true, then you activate this block. If it is false, you activate this block, right. So, the control and the data flow graphs, they are being generated together side by side, and whatever you have for the control, there will have to be a segment of the data flow graph corresponding to each of them, each of those nodes.
So this is x equal to 1, right?
No, this if x equal to 0, they do this, otherwise do this. This is the block you execute when x equal to 0. This is a comparator. The comparator will be returning true if x is 0. It will be returning false if x is not equal to 0. Okay. So, this is how a simple if statement in the behavior description can be handled. Now, there are certain ways in which you can optimize the piece of hardware, and we can get, you can say, a more efficient relay. Suppose you consider this same scenario, this same example. There are 3 blocks. One is a comparator block, this is a computation block, a subtractor, this is a computation block, add a subtractor. Now, suppose we want to combine these 3 together. So, this combining these 3 together, how do we do this? So, actually what we are trying to do now is that we are trying to, well, again the control flow description was different, data flow description was different. Now, we are trying to synthesize. I am showing you typically the output of the synthesis, that how this control and data flow can be taken both together, and a register level netlist can be generated. So, for this particular example, I am showing the final diagram. Just for your reference, this was the description. Now, in the earlier one, you see this was the comparison, okay. This is there, read x 0, compare with this, and the else part, there was a d equal to d minus 1, this has been computed here, read d, subtract 1 from it. So, this computes d minus 1. Okay. Similarly, if x equal to 0, you have a equal to b plus c and d equal to b minus c, b plus c. So, here you have computed something which is the value of it's actually b plus c, and b minus c you are computing here, this is b minus c, right. Now, the synthesizer will come to know that if x equal to 0, the value of b plus c has to be assigned to a, and there is no conflict here, there is no other assignment to a. So, you put a multiplexer here, depending on the result of the comparison. If it is true 1, then this b plus c will be stored into a, but if it is false, see this description says if it is false I am not assigning anything to a. So, actually as part of the data path, either there are two ways, either you disable write a, or you just introduce a dummy read a and through this multiplexer write back the value of a. Both way can be used. And similarly for the other part, for writing d, if the result of the comparison is true, then you write b minus c, otherwise you write d minus 1. Right. So, this diagram essentially combines both control and data. In fact, this is CDFG now, control data flow graph both together. So, this I have drawn just for the sake of convenience. Actually in the implementation these registers will not be scattered like this, there will be some register bank kind of a thing, there will be some reads and writes generated for that, it will be more complex, but just for understanding the basic concept I have shown you these examples. Now, one thing I told you that after this data flow or the control flow graphs are constructed, well, control flow graph will reflect the control information. Now, data flow graph or the different segments of the data flow graph can be combined using control flow information, as this example has shown you, because earlier we had different segments of the data flow graph. Using control flow information, we have been able to combine them into a single one. Now, after we have done this, we can carry out several transformations on this in order to optimize. Now, in fact, these kind of optimizations are fairly standard and are already used since a long time by compilers. So, we call them compiler transformations. We will see that what kind of typical transformations are carried out. Now, as you can see that some of the transformations are constant folding, redundant operator elimination, tree height transformation, control flattening, logic level and register transfer level transformations. So, these are fairly standard things which are applied on a given CDFG in order to get another CDFG which is better. So, intermediate representation still remains CDFG, okay, CDFG to CDFG transformation. Okay. First, let us try to explain constant fold. It is a very simple thing. It says that in many cases you will see that there is a portion of the CDFG where there are some portions which can be immediately evaluated. There is a constant 10 and a constant 4. Suppose there is an operator subtraction which you are writing somewhere. So, the processor can immediately find out that there is an operator for which the operands, the values of which are already known. So, it can evaluate it at the compile time itself, and straight away you can transform it into a constant value 6 which you are writing into A. So, you do not need a subtractor, you do not need places to hold 10 and 4, straight away you can write 6 into A, simple. Redundant operator elimination. Well, this already we had illustrated in an example earlier, but let me show you again with an example. Suppose we have two statements z equal to x plus y and w equal to x plus y. So, obviously you can see that this x plus y is a common operator. So, with respect to the DFG, the kind of transformation that will take place is this. In the original diagram, it will be something like this. Write z. This is for z, the first one, and for the second one there will be again a similar block generated. Sorry, w, write w. Okay. So, these will be the graphs which are generated initially before any optimization steps, but the processor can find out that there is a portion of the tree read x read y plus, these are identical. So, it can identify this redundant operator or means common operator or common sub expression, whatever you call, and it can transform this graph into another which will be like this. Read x read y, add write z, write w. So, the same value you are writing in both places. So, this is one standard method which is used. Fine. And there is another method which is called tree height transformation. This is actually important from the point of view of efficiency in execution of the synthesized hardware. So, actually this also I am explaining with an example. Suppose I have a statement like this: A equal to B minus C plus D minus E plus F plus G. Suppose corresponding to this, well, I am just showing the DFG, okay. After parsing, the DFG is constructed. Say the DFG has been constructed like this. I am just showing the DFG, I am not showing the entire part of it. Subtraction, I am showing in the reverse order, okay. B, addition, then C, again subtraction, D, again addition, E, another adder, F and G. So, in this way the computations are carried out: F plus G plus E, D minus this, C plus this, B minus this. So, this finally will go into A. Okay. So, this okay, this in terms of the intermediate computation, how many steps you need for this? Of course, you need 1, 2, 3, 4, 5 steps. So, this will need 5 computational steps, because the way you have drawn the computation tree, the computation has to be done in sequence.
Isn't that it is subtracting D from D plus F plus G from D?
Huh?
Bracket out C to G.
Okay, okay.
E to no.
Yeah, like this. Yeah, this. Fine. E plus F plus G are together. D minus this. Again. Yeah. Great. Fine. So, as an alternative, what we can do? We can try to find out what are the things we can do in parallel. In this example, for instance, you can see f plus g and c plus d we can do in parallel. So, we can have an adder with c and d, we can have another adder with f and g. These two can be done in the same step. So, we have done this, we have done this. So, now we will have to add e to this. We need another adder with e. We have computed this. So, this minus this. Similarly, lastly, there will be another subtractor b minus this. So, here we have been able to save one step, 4 steps. Now, in general the number of steps can be reduced even more, but one thing you try to understand here, because this is also a very important part of high level synthesis. The point to note is that by rearranging the way we are carrying out the computation, we have been able to reduce the number of steps. But in the process, are we having to pay something more?
So parallel computation
Parallel computation is fine. One thing you note, in the previous case, since the operations had to be done in sequence, then we could have used a single adder subtractor hardware for the purpose. But here we would be needing 2 parallel hardwares, 2 adders are needed. Well, we can save time, but we will have to use multiple copies of computational hardware. So, this is a price to be paid, this is some kind of a trade off, that if you need higher speed, we will have to invest in more hardware. So, we will see that there are some trade offs involved. There is a step called control flattening. Of course, see, this step of control flattening is useful only for the purpose of control unit design. The idea is simple. See, whenever you have a very big system or circuit and you are trying to design the control unit for it, there are 2 approaches. One is that you generate the control specification for the whole circuit and you start, or you go about generating the FSM for generating the control signals all in one go. But in many systems, particularly for large systems, processors, you will find that there is a hierarchy of control which comes very naturally. Like, I am giving an example. Suppose at the highest level you can say that in order to perform a task I need these 4 things to be done in sequence. So, let us generate 4 control signals for these 2, one after the other. Now, the third control signal, for example, this is meant to excite a piece of hardware which in turn is a slightly complex system which requires 4 steps internally. So, those 4 steps I could have embedded in my original control specification also, but as an alternative I can also have some kind of a hierarchy, that in the high level description there are 4 steps, but within the third step there are again 4 sub steps. So, if we can specify it like this, our control specification and implementation may become easier. Otherwise, our control specification will become very huge and we can end up in designing one single very big FSM. But instead, several smaller FSMs may be more efficient, both in terms of area and execution. So, control flattening I am illustrating with an example. This I already have the diagram here. Suppose we have a control flow graph like this. This is not really a control flow graph, I have actually shown both of them, also data flow computations are shown here. Suppose this is a data flow computation block, after that there is an if statement, depending on the outcome of the if, either you come here or come here. So, here again there is some data flow block, another if statement, data flow block here, data flow block here, another if statement, you come out. So, you can take this entire graph at one go and try to generate the control signal. But for that purpose, you try to understand what will happen when we are trying to generate signals to activate, say, these blocks. You will have to know the outcome of this if statement, you will have to know the outcome of this if statement, you will have to AND them up together, then you will have to generate the signal for the multiplexers or whatever. More you have nested ifs and those things, this problem will become more and more complex. So, it is not just one if, there are actually several conditions you need to see together in order to decide whether you have to do this or do this. Because ultimately this is a piece of hardware which have to be activated using a single control signal, just unlike a program execution where you can have several if statements. So, what you can do, you can define this sub block as some kind of a macro block. And at the high level you can treat the diagram as like this is a macro block. So, if the if statement is true, you activate the macro block. So, at this level your control becomes very easy. But inside the macro block there will be another level of control. Checking of this and activating this will be inside this macro block. So, actually you are now having some kind of a hierarchy of control signals being generated in a hierarchy of modules. This helps in many cases. Instead of having a very big, see, bigger the size of FSM, more number of flip flops you have to need to store this state, more amount of hardware will be need to generate the control signals out of those states. But if you have this hierarchy which can come very naturally from a description, it can help a lot. And you can have some kind of logic level transformations which are of course fairly trivial, like I am giving a very simple example. Suppose in a portion of the data flow graph you have a segment like this. So, you are reading the values of two values A and B. Suppose you are doing a logical NOT on one of the values, then you are doing a logical AND on this value and B, then you are doing a final OR on this and this to generate, say, a value C. Suppose this diagram came out directly from your hardware description. So, actually what you tried to specify was C equal to A or A prime B. Now, the synthesizer can very easily find out this expression, optimize it, it knows that this is equal to nothing but A or B, and it can simply modify this diagram as sorry, this is OR. Okay. So, this kind of simple logic level transformation will carry it, but as you can understand, for this purpose you need a logic optimizer like Socrates or MIS, which we have already mentioned. This will be also part of the story. The synthesizer will be invoking them to optimize the logic part of it to get an optimized version of it. Okay, and finally, we can carry out some register transfer level transformations. Now, let me illustrate this with an example which you already have on a diagram. See, register transfer level transformation means, see, there can be some peculiarities or some special functionalities of the basic hardware elements you are using, and you can utilize them to get a better realization. Like you look at this example. Say in this example you have two operands A and B, which you add them together. Finally, you add 1 to it and write it to C. So, you are actually trying to compute A equal to C equal to A plus B plus 1. So, if you want to directly map this into hardware, you will be needing two adders. The first adder will be adding A and B, the second adder will be adding 1 to it. Well, either you do this or you do it in two different steps using the same adder. But the synthesizer will observe that, well, the adder that we have, that also has a carry input. So, if I set the carry input to 1, then this addition by 1 is taken automatically care, this can be automatically taken care of. So, I do not need this additional step of adding 1 by using a separate function unit. So, rather these two adders I can combine by a special operator add increment, which also I can implement using the available adders. So, this can be transformed into an add increment operator kind, where AB add increment write to C. So, in this case actually the carry input will be set to 1, AB will be coming and the output, this will be your C, C will be computed. So, this kind of transformations, as you can understand, are very much dependent on the capability of the available hardware which the synthesizer will be using, right. So, today in this lecture we have tried to give you some idea regarding the CDFG and what kind of transformations can be carried out to optimize the CDFG. But we have not yet talked about the systematic procedure that one may follow or use in order to synthesize the hardware starting from the CDFG. This discussion we shall be starting from our next lecture. Thank you.